If you're worried about proof for your upcoming A-level exams, I've got 4 exam-style questions to make that less of a worry. Hi, I'm Martin, an A-level teacher of over 7 years, committed to supporting students in their learning of maths, in particular A-level. Right, let's get started. Given that n is a natural number, prove that n squared minus 2 is not divisible by 9. Now, firstly, just might be worried about wondering about notation here. So, as I said, this means n is a natural number. So that's just all your positive whole numbers, 1, 2, 3, 4, etc. So we're going to prove that n squared minus 2 is not divisible by 9. Now, obviously, we're not going to do this for 1, do this for 2, do this for 3, and carry on, because obviously that would be, we'd be doing that for all infinity. So we're going to split this up into 3 different categories to save ourselves a little bit of time. We're going to split all of the numbers up from 1 to infinity into numbers that are multiples of 3, numbers that are multiples of 3 plus 1, and numbers that are multiples of 3 minus 1. The reason why I'm splitting up the numbers like that rather than just even and odd is because I'm looking at this being, showing it's not divisible by 9. If I just do even and odd, when I sub even and odd numbers into n squared minus 2, I'm not going to be algebraically be able to show whether or not they're divisible by 9. But because 3 is a factor of 9, this is a good sort of method to approach here. Okay, so we'll see, hopefully, you'll see why it will work in a second doing that. So we're going to start off by saying let n equal 3k. So these basically just are all your multiples of 3. So 3, 6, 9, 12. So that's going to cover a third of all numbers from 1 to infinity. Okay, I'm just going to define there that that k is a natural number as well. So what we just do is we substitute the n, we'll replace the n with 3k. So 3k bracket squared minus 2, well, that would equal 9k squared minus 2. So what we've clearly shown here is we're doing 9 times a number. Okay, and it's trivial. We don't need to prove why, but here in the exam, but because k is a natural number, that will also mean that k squared is a natural number. So 9 times a number is a multiple of 9, but then we're taking away 2. So we can conclude that this is not a multiple of 9. Okay, so that's a third of all numbers. That's 3, 6, 9, 12, etc. done. What about the next set of numbers? So what about multiples of 3 plus 1 here? Okay, so this is going to do 1, 4, 7, 10, etc. So this time, so I'm testing 3k plus 1. So I'm going to substitute the n, replace the n with 3k plus 1 here, and take away the 2. So then expand that bracket out. That's going to be 9k squared plus 6k plus 1 when I expand that bracket out. Don't forget to take away the 2. And then what I'm going to do is the first 2 terms, I can take out a factor of a 3 here. Okay? And then 1 minus the 2 is minus 1. Okay? Now, I know the question's talking about whether or not it's divisible by 9. However, if I can show that a number is not divisible by 3, then it can't be divisible by 9. So what I've shown here is this number, when I do 3k plus 1, this is not a multiple of 3, so cannot be a multiple of 9. It's really important that you do these mini conclusions, as I call them, throughout. Okay, so you need your overall conclusion at the end, but just make sure you're doing these mini conclusions as you go along. So just showing that you're saying, okay, numbers in the form 3k are not multiples of 9. Numbers in the form 3k plus 1 are not multiples of 9. The final thing to do is we're now going to let n equal 3k minus 1. This will basically be 2, 5, 8, 11, etc. So By the way, I've used 3k minus 1. You could do 3k plus 2. That would also be valid. However, I just personally think if you've just done 3k plus 1, doing 3k minus 1, it is probably going to be a simpler way to go about this. So if we expand the bracket there for 3k minus 1, you'll get 9 squared minus 6k plus 1. Don't forget to take away 2. Sometimes people forget, do the expanding part, but then just forget about these constants at the end. And what I'm going to do again is take out a factor of 3 for the first two terms. 1 minus 2 is minus 1. And you can show there that this, yet again, is not a multiple. Not a multiple. It's me talking and writing at the same time, just spotted that. This is not a multiple of 3, so cannot be a multiple 9. So if we've shown that all the multiples of 3 are not multiples of 9, or the numbers that are multiples of 3 plus 1, when you plug it into n squared minus 2, if they're not multiples of 9, if when you do it for multiples of 3 minus 1, that doesn't work either to be a multiple of 9. So therefore we can conclude that n squared minus 2 is not divisible by 9 for n being a natural number. Next question, we're going to do some proof by contradiction. This in particular is one of the parts of proof that people find difficult. So hopefully after this, and we've also got another one coming up in a second, hopefully this will start to make it a little bit nicer. So these sorts of questions have been coming up in papers, whether that be A-level or international papers. So I really wanted to pick one like this. So we're going to prove by contradiction that there are no positive integers x and y such that 2x squared plus xy minus y squared equals 6. Okay, so you can't put in a positive integer for x and y to make that work. So what we would do first is we start by making an assumption. So we'd say assume that there are positive integers x and y such that 2x squared plus xy minus y squared equals 6. Okay, what we do with proof by contradiction is we try and say, okay, well, let's assume it can be done, and we'll then try and take some logical steps. But then if we see that, we can't do that, we'll see hopefully in a second, we get the case where it all breaks down, then we have to conclude that the original statement was actually true. Okay, so we're going to show that, let's say it can be done with positive integers. Now, what I would do here, I've got this 2x squared plus xy minus y squared equals 6. What I'd do is I can factorise that. Might not be the most obvious thing when you first see it, but 2x times x will make the 2x squared. As for the minus y squared, if you have a plus y and a minus y, you can make that work. We just need to make sure we get them in the correct bracket, so you can expand that back out to check that works. And that's going to equal 6. Okay, now x and y are integers, so that means that when you times an integer by an integer like 2, or if you just add or subtract integers, they will still be integers. Okay, so what I have in my brackets have to be integers. So I'm looking for two numbers that multiply together to make 6. Okay, where both those numbers though have to be integers. So 1.5 and 4. That's off the table here. So if I look at the pairings, I've got 1 and 6. Also, I'd have 6 and 1. I'd have 3 and 2. And I'd have 2 and 3. Okay, I'd also have minus 6, minus 1 if we were told that they're just integers, but we're talking about positive integers here. So we don't need to worry about the negative numbers. So it'll just be 1 and 6, 6 and 1, 2 and 3, 3 and 2. So what I'm going to do first is I'm going to start off by showing what happens when we have one of the brackets be 6, the other be 1. Just looking at all those combinations. So 2xy equals 6, x plus y equals 1. And if I try and solve this simultaneously, so just add the two together, I get that x equals 7 over 3. Okay, well, that is not a positive integer. I guess with this one as well, you could argue logically that x plus y can never equal 1 anyway, because if x and y are positive integers, then at the very least you'd be doing 1 plus 1. So you could argue that as well, but I've just done it there with the simultaneous equations. Okay, scenario number 2, 2x minus y equals 1 and x plus y equals 6. Well, let's add them together. And yet again, you get that x is 7 over 3, and that is not a positive integer. That didn't work. So now let's look at scenario number 3. 2x minus y equals 3, and x plus y equals 2. So you've got 3 in one bracket, 2 in the other. And yet again, I'm going to add both equations together. And I get that x is 5 over 3, and that's not a positive integer. So not looking good for saying that x and y are positive integers. And then the last roll of the dice is to see if 2x minus y equals 2 and x plus y equals 3. And that doesn't work either. Okay, no, there's no need to go on to find y here, because if x isn't a positive integer, then there's no need to find y either. And as I mentioned, we don't need to do minus 6 and minus 1 because we know that x and y are positive integers. So we could just say like a little statement here. If x and y are positive, x plus y can only be positive. So no, I've done it again with spelling. I've spelled positive wrong throughout here. It's me talking and writing at the same time. So x plus y can only be positive, so no need to test negative pairings. I'd hope that you listen to me for maths advice, but not for spelling advice. So we can conclude that from what we've shown there are no positive integer solutions to 2x squared plus xy minus y squared equals 6. Okay, so we've shown the contradiction there is that every time we get something that's not a positive integer, so it cannot be done. Our third question, if I need to make this a little bit smaller way, make sure you check out the questions that are attached below. So I've got the PDF with all the questions on, so do have a go at those. So for this question, we've got a student was asked to prove by contradiction for x being a natural number that if x cubed is a multiple of 5, then x must be a multiple of 5. The start of the student's proof is shown in the box below. So this is pretty much based on an actual question that I saw from one of the international A-level papers. So you've got there, if the assumption is there exists a number x, where x is a natural number, such that x cubed is a multiple of 5 and x is not a multiple of 5. So we start off by considering x equals 5k plus 1, do the proof there to find that it's not a multiple of 5. We do it for 5k plus 2 to then show that it's also not a multiple of 5. So we're going to show the calculations and statements that are required to complete the proof. So this is one of these cases where it's partly been done because it would be quite time consuming to do all of this, and by kind of doing 5k plus 1 and 5k plus 2, it should save ourselves a bit of time. So what we're doing here, this is kind of a mix of contradiction and exhaustion when we're doing this. So we're assuming that x is not a multiple of 5. So already what the student has done here is they've tried numbers that are 5k plus, in the form 5k plus 1 and 5k plus 2. So, that's your 1, 6, 11, things like that. Multiples of 5 plus 2, so that's your 2, 7, 12. What we now need to do is do numbers that are multiple of 5, 1 minus a multiple of 5 minus 1, or multiple of 5 minus 2. So we're going to start off by saying let x equal 5k minus 1. As we talked about in question 1, you could do multiples of 5 plus 3 and multiples of 5 plus 4. So instead of doing 5k minus 1, I could do 5k plus 4. That would cover the same numbers. However, why do a harder calculation with 5k plus 4 when they've already done 5k minus 1? Sorry, they've already done 5k plus 1 for us. And that will be very similar when I come to expand it. So I'm going to say, let 5k minus x be 5k minus 1, where k is a natural number. So I'm going to consider x cubed is 5k minus 1 cubed. And when I expand that out, so that's going to be very similar to what they've done in the question. But when you get to the k squared term and the constant term, they're going to be negatives instead. Okay, so you could very quickly expand this with using Pascal's triangle or binomial expansion anyway. But basically what's going to happen here when you use the binomial expansion is that k squared term, well, you're doing 3 choose 1 times 5k bracket squared, and then you're going to be timesing by a negative 1. So that's why it's going to be minus 75k squared. When it comes to the 15k, that will still be positive like it was before, because you'll be doing 3 choose 2 times 5k times minus 1 squared. So because you're squaring a negative, it's going to be positive. And the final term is just minus 1 to the power 3. So that's going to be minus 1. So then you can just factor out as I did before. So it's, it might seem that it was going to be quite daunting, this question, but actually, because I've already given you part of that in the lead up to it, you can quickly kind of just pretty much copy mostly what they've done, but just change signs where need be. So this is not a multiple of 5. So then what we do is we then let x equal 5k minus 2. Again, it's possible you could do 5k plus 3, but let's use the fact that they've done 5k plus 2 for us. So we do a very similar thing. Not x, sorry. Make sure we do it for k. Oh, that's a mistake in the question. They should be k's. They should be k's. They should be k's. That's why I'm gonna in future questions I'm gonna just use actual exam questions rather than ones I've made myself, just for those sorts of reasons. So you've got there everything in terms. You've got expanded that out there. And yet again, very similar. It's just going to be your k squared term and your constant term that are going to change. So I'm going to factor out a 5 here. Now for the minus 8, I can say, well, that's minus 5 minus 3. So I'm going to put a minus 1 there, just to show that it's all just a multiple of 5. I think you'd be fine if you just had the minus 8 on the end. It should be pretty trivial that is not a multiple of 5. But basically you're doing 5 times the number, but then you're minusing 3, so it's not a multiple of 5. And then I'm just going to carry, obviously in your exam, don't write all over the place. Make sure you write this below. So for all cases where x is not a multiple of 5, okay, this is why we didn't do, if you're wondering, this is why we didn't do 5k. Okay, we're just showing where x is not a multiple of 5. That was our part of our assumption. So for all cases where x is not a multiple of 5, x cubed is also not a multiple of 5. This is a contradiction. So therefore I can conclude that if x cubed is a multiple of 5, x is a multiple of 5. Okay, so that's 3a done. Now what we're going to do is go on to part B of this. Okay, we are going to prove that the cube root of 5 is an irrational number. Okay, so a rational number, a number that you cannot write as a fraction where, if you write it as a over b, a and b cannot be, you can't have that with a and b both being integers. Okay, so our assumption therefore, so we're going to assume the cube root of 5 is a rational number. Okay, so if we're trying to prove it's a rational number, well, let's say, okay, well, if it's not an irrational number, then we'll start by assuming that it is a rational number instead. Okay, and if I can show that that's absurd, if I can show that it can't be a rational number, then it has to therefore be an irrational number. So we'll say that the cube root of 5 is a rational number such that, just kind of going into that definition of being a rational number, the cube root of 5 can be written as a over b, where a and b are integers with no common factors other than 1. Okay, so what we do is we start by writing the cube root of 5 as a over b. Okay, so the cube root of 5 equals a over b. Okay, that's what it would mean if it was a rational number and a and b are integers. So if you cube both sides, then 5 is equal to a cubed over b cubed, which means a cubed must equal 5b cubed. Well, this means that a cubed is a multiple of 5. Okay, so a cubed is a multiple of 5. And what do we just say about multiple, if something cubed is a multiple of 5? Well, this is why it's a hence question. So if you see the word hence, think about what am I going to use from previous to help me do this. So if a cubed is a multiple of 5, then a is a multiple of 5. So if a is a multiple of 5, well, let's say let a be 5k, where k is a natural number. So going back to the a cubed equals 5b cubed line, we're going to replace a there with 5k, and 5k in a bracket cubed, that's going to be 125k cubed, and we can divide it by 5 to show that b cubed equals 25k cubed. So b cubed, let's take out a factor of 5. So b cubed is 5 times an integer. Okay, if k is an integer, k cubed times 5 would be an integer. So what we've just shown there is b cubed is a multiple of 5, which means b is a multiple of 5. Well, that is a contradiction, because we said that a and b have no common factors other than 1. So we could just put a conclusion there. This is a contradiction, as a and b have a common factor of 5. Okay, they're both multiples of 5. Okay, and we're saying that, this is basically a simplified, we can write this rational number as we should be able to write it as a simplified fraction. So we can then conclude, therefore, the cube root of 5 is an irrational number. So that's number 3 done. What we're going to do now is look at our final one. We're going to look at question 4. So we're going to prove that for all positive values of x and y, 4x over y plus y over x is greater than or equal to 4. And then there's a bit of proof by counterexample at the end there. So what I should do for these is I should sort of play around with it first. Okay, play around with your maths. I'm a big advocate for just playing around with it, seeing how far you can get. So we're going to play around with it some first until we find a logical starting point for it. So we're going to just, and this, when you're proving things, you shouldn't just be starting with the proof and working it backwards. So this isn't the proof, this is just my rough working here. Okay, until I find that natural starting point. Because if I showed you what the proof is, with the starting point that I'd pick, you'd be like, why are you starting with that? That seems a bit random. So hopefully you'll see why I end up picking the starting point that I do. So I just play around with this, and what I might think is, well, let's just combine the fraction. That seems like something that might help us get somewhere. So if I combine this fraction together, just add the fractions together, combine it into 1. Basically, I'm looking for a common denominator there of x, y. So I've times the denominator of the first fraction by y, so I need to do that to top as well. By x even, so I need to do that to top as well. So I've got 4x squared. The second fraction, timesing that by y, so times the bottom by y, so also times the top by y. So that's how I've got to that stage there. And then I'm going to times both sides by xy. Okay, which gives me the following. Now, something to be really careful here and to mention, I can do this since x and y are both positive, okay? Because if x and y weren't both positive, I don't know what their signs are. If x and y are negative, then I need to change the direction of my inequality sign. However, not a problem, because I know that x and y are both positive. So then what I'll do, let's just get everything to one side. And then I might look at that and go, well, can I factorise this? Is my next question. And the answer to that is, yes, I can. Okay, you get, if you have 2x in both brackets, that makes you 4x squared. If you have minus y in both brackets, that's going to make you positive y squared. And then timesing it all together, you'll get two lots of minus 2xy terms. So that works, and they're both the same factor. Okay, you've got a repeated factor there. So we've got 2x squared minus y, 2x minus y, squared is greater than or equal to 0. So this is going to be my starting point for the proof. Okay, so this is the actual proof that I'm going to do here on this right-hand side. And basically, I'm just going to do this all but backwards, and just explain a few extra steps along the way here. So I'm going to start off with this statement, which I know to be true. 2x minus y in a bracket squared is greater than or equal to 0. Okay, and I'm just going to put a little comment here that this is because since any number squared is greater than or equal to 0. Don't forget about that last part, that you can square a number and it not be positive. Okay, because you can square 0 to get 0. Sometimes a thing that people miss off, and we do need to be that particular because we are talking about proof here. So 2x minus y bracket squared is greater than or equal to 0. That is something we can't argue against that. So then you expand this out, and this is actually really easy from this point because you've done all this work. You're just basically doing it all backwards from what you're doing on the left there. So I'm pretty much just writing out these steps that I had from before, but just kind of going backwards now. One key thing here though to mention is that at this point here I'm going to divide both sides by xy, and it's really key that we mention about the fact that x and y are positive. So we'll put here again, since x and y are positive, this doesn't change the direction of the inequality sign. Okay, it's just really important that we mention that. Okay, and then we're pretty much there because we just divide both sides by x. We divide both terms on the top by the xy. So 4x squared divided by xy, you get 4x over y. And then y squared divided by xy, y is going to cancel, so you just got y over x. And we're just showing that's greater than or equal to 4. So just put that little box there to show that I have completed the proof there. So then finally, we're just going to prove by counterexample that this is not true if x and y are not both positive. So that doesn't mean that they both have to be not positive. It just means that just at least one of them needs to not be positive. Okay, so you don't need to do x and y is negative. You can just do x is a negative number, y is a positive, or vice versa. So let's just try some numbers. So let's look at when x equals 1 and y equals minus 1. Let's just evaluate that left-hand side, LHS for left-hand side. So we've got 4 divided by 1 plus minus 1 divided by 1. And when we do that, this is minus 1. 4 times 1 divided by minus 1. So just replacing x with 1, y is minus 1. And when I do that, minus 4 minus 1 equals minus 5. Again, in the exam, please write below what you've done, but I'm just going to carry this on to the right hand side here. So minus 5 is not greater than or equal to 4, as the inequality suggests. So does not work for x equals 1, y equals minus 1. Okay, so just for a counting example, I just need to show one case where it breaks down, and then you can't claim that that is always going to be true if it breaks down for even just one example there. Next time we're going to look at parametric equations, and I'll put a link to those questions in the description below. If you want to have a go at some calculus problems that I did a couple of years ago, some YouTube shorts, I'll put the link here, so you can click here for that. Or if you want to just do some general calculus practice, some longer questions, there's also a link to a video for that here. But I hope you enjoyed this video. If you've got any questions, let me know, and see you in the next Maths with Martin video.